Okay, so I'd just like to make a quick clarification note about the notation I was using during the lecture of Rice's theorem. So remember, during Rice's theorem, during that lecture, we were discussing properties of CE languages. So in properties of CE languages, I was given some language, which was CE, and P mapped that language to either true or false, meaning that that language either did or didn't satisfy or have this property, okay? And this was a function. This mapping was a function, right? So given some language, then P would map to one and only one value, either true or false, right? So for example, P of L1, if L1 was a C language, then P of L1 might evaluate to true, whereas P of L2 might evaluate to false, okay? And this was the definition of a property of CE languages. What I had done slightly later on is that I had given this other theorem where I was talking about the implementation independence of properties of CE languages. But really, when I was doing this, I was implicitly assuming that we were discussing decision problems where the decision problems were about properties of C languages, but what we were given as an input, was a Turing machine. And that's been the case in all of the decision problems that we've studied, right? Even though these decision problems have been about the languages, for instance, L being sigma star or L being the empty set, the input instance to that problem has been a Turing machine. And that's because we have to finitely represent, or we have to give a finite representation to a CE language to begin actually answering or solving the decision problem. So really, what I meant in this theorem, and it's really just an abusive notation on my part, is we meant to say some language over the alphabet sigma and some property P sub m, right? So I should have really used a slightly different notation. So in this case, perhaps P sub m would have been appropriate, where we say of a language L, where this property P sub m has an additional parameter. So m is an additional parameter, where m is a Turing machine such that L of m is equal to L. So a property P sub m of some language where we're discussing a particular Turing machine that is representing that language. This property, which accepts a language but which is additionally parameterized with a Turing machine, is a property of C languages. So we could have said P sub m here. If and only if, for any pair of Turing machines that accept the same language, if we give that same language to P, but we use M1 or M2 to represent that same language, the answer, the evaluation to that property will be the same. And so really you can think of this as an alternative definition to what a property of a C language is. So like I was discussing during the lecture, instead of this being a theorem, you could also think of this as an alternative definition to what a property of a C language is. And this is because when you're dealing with a C language, you need to deal with some concrete, finite representation of it to be able to do something with it, right? Because if I'm asking is this C language equal to sigma star? Well, even to be able to check this, right? Even to be able to check this, if this was somehow decidable, you would need, say, the Turing machine that accepted L to actually check that, right? You can't just start with L, because how is L represented? Are you using an infinite set? Or are you using the lambda calculus? Or what are you using to represent L? Okay, and so this is the slight abuse of notation that I made throughout this lecture. And so when you see something like P of L of M, you can safely assume, and you can even check that just to be sure, that I'm really just talking about the property of L of M, but when I'm discussing this language parameterized by M, right? So that's really why I was dealing with L of M and not just L, because I was talking about the Turing machine M, which was representing the language L of M. Okay. So of course this is a language, but now M is the Turing machine which accepts or represents that language, which accepts that language. Okay. Okay, and so hopefully this makes a bit more sense in terms of clarifying notations. And so for instance, even on this right-hand side here of the if and only if, or of this definition if, alternatively, really what I'm saying is that this property is implementation independent if, when I'm using, say, the Turing machine M1 to represent L, which is L of M1, if that property evaluates to true, then that property of that same language must also evaluate to true when I'm representing that language at M2, and vice versa, right? And vice versa. And so that's why when I did this example here, I was saying, well, let's be given some Turing machine M. Let's be given some Turing machine M, which accepts some C language, because what I'm saying is that I have a C language, yes, but it's represented through some Turing machine. And what this shows is that it doesn't matter what Turing machine I'm using to represent that language L. Whatever Turing machine I'm using, the property is going to evaluate to the same thing given the language accepted by those two Turing machines, right? So the property evaluates to the same thing regardless of what Turing machine I'm using to implement the acceptance of the language L.